Okay, so welcome everyone to lecture 18 of our series CS2 classes. And I guess in the last lecture, we just had a look at what happens if we incorporate excessive loss reinsurance. And if we are looking at compound distributions, right? Am I sharing my screen? Yes, I am. Okay. Yeah. So we had a look at how artificial it is to sum up these Zs for the reinsurance company. Why? Because sometimes this Z also takes the value of 0. And this 0 value may not always be, within the information set for the reinsurance company. So we saw that it's always better to have a look at W, and instead of N, remember we defined a new random variable, which is NR, which represented the number of non-zero claims for the reinsurance company. So basically the total number of claims that reinsurance company gets to know about. And then we had a look at its moments, which was expectation of SW. Then again, to define expectation of SW, we were supposed to calculate expectation of the NR. And for that, we had to define NR in terms of N, because we know a little bit about N and we really don't know about NR. And this is what we're trying to get to know about using the information that we are aware of, which is about N. So we used indicator variables or dummy random variables like I, defined here to take value 1 if my claim amount is higher than the retention limit and 0 otherwise. So again, maybe in general econometrics perspective, in those aspects, you can alter these 1-0 definitions, or sometimes you can even take 2-0 instead of 1-0. But over here, it is very strict that it will be 1 when x is greater than n and 0 otherwise. So it cannot be anything else than this. Otherwise, it would change the whole definition of how we define NR. So then we saw that, basically our I is Bernoulli with pi, and that is just binomial with 1 comma pi. And we derived the MGF and the MGF not only for NR, but using NR's MGF, we derived the MGF for our S guy as well, right? SW here. And remember, SW is just SR. So they are not defined in the same manner, but the value they take is exactly the same. Because for all the other values, for all the other Zs, wherein you do not have corresponding W, it's 0. So it actually adds up to 0 again. So not really much of that there. And the very good thing to remember over here is the distribution of W that we derived in the reinsurance chapter. So remember, you don't have to recall the formula as such. Just remember the way we are defining W, what exactly is W. Remember, it is not just x minus n, but it is a conditional random variable conditioned upon the value that my claim amount is higher than the retention limit. And this is how we define its distribution function, the probability distribution function for W. So I guess I've written F of W here, but I used G elsewhere. So it's just a matter of notation. And then we had a look at this nice sum, which was just an application of what we studied and a very good example and know how to use this W to figure out this stuff about SW and about NR as well. So I guess did you guys calculate the variance and everything else? Yes, did you guys get a chance to figure out the rest of the stuff which we probably didn't cover in the lecture? Can you guys hear me? So I guess that means no from everyone. So I would say, if you feel comfortable with these calculations, no need to solve them again and again because it's just the same. It's just that you put a square of over x and m and you derive the same thing. But again, if you want to be more comfortable with such calculations, then I would suggest that it is really a good practice to figure out stuff and check where you might go wrong. Okay, so that's there. But again, it's up to you. I cannot really force anyone to sit and practice over there. So, okay. The next thing that today we are going to study is individual risk model. So remember at the very start, we defined two types of risk models, right? One was collective risk model and the other was individual risk model. Does anyone remember the key differences between these models?
In individual risk model, we know the number of claims.
Exactly. And any other difference? That was the crucial difference. Thank you very much.
X is independent but not
Yes,
identical.
so exactly right. So here, when I'm talking about one particular X, it represents one particular contract, which is one particular policy. So I say that, they are only independent and they need not be identical. And again, if they are identical, then what happens is it behaves as a collective risk model. So, but not always again. So there are the specifications. And I think it's just a matter of, question mentioning the number and the question defining the distribution for that one particular n random variable that we are looking at. And you would just know whether you're looking at a collective risk model or an individual risk model. So that's there. And again, so the kind of individual risk model that we are going to study in this chapter is a very restricted form of, I would say, a generalized individual risk model. So again, just summarizing certain assumptions here. So the very defining aspect is that we have a fixed number of risks here, right? So we have a fixed number of risks. And when I'm saying number of risks, I mean all of those x's that I add. So that's x1 is one risk, x2 is another risk. This could be really a good tongue twister. But yeah, okay. So the main assumptions that we have to look at are that the risks are independent. So these are basically the general assumptions that I'm going to make. So there will be three general assumptions. This is first. And then I'm going to say that, claim amounts need not be identically distributed. And the third one is that, so again, because I have a fixed number of risks, I know that my number of risks will really do not change, right, over the period of insurance cover. So my number of risks is fixed. Again, I mean, that's just the repetition. So these three assumptions are always true wherein we're considering an individual risk model. But for the purposes of this chapter, we add two more assumptions which make this model really restrictive. And the very first of them is that the number of claims that I can have from one risk. So basically, let's say I'm defining just give me a minute.
Ma'am, you are not audible.
Oh yeah. Sorry, I was unmuted myself, right? Okay. So what I said was, I said that I'm adding up these x's, which are individual risks, to get to a random variable, which is y. Okay. And then what I do is, basically, I'm citing the assumption, the very first assumption that we make, which is about the number of claims from a particular jth risk, which might be x1, x2. So I'm representing xj here. And when I talk about jth risk, it can be anything from 1 till n. Which, so the number of risks will either be 0 or 1. And just basically writing this assumption diverts our mind to believing that this can only be applicable in respects to life insurance cases, right? Because if we have a general insurance case, then I know that I can, I mean, there is no certain restriction in the number of claims that I can claim for a particular policy that I have taken or a particular policy that I've invested in. So here when I'm restricting that one can be the maximum number of claim, one can, a policyholder can claim onto each risk, then I know that I'm looking at specifically life insurance cases where the claims generally, I mean, always do not exceed one. And the next thing is, and this is not an assumption, but just a fact. So the probability that you will observe a claim. So the probability that you observe a claim from jth risk is just qj. So remember the way we defined pi in the previous case, which was the probability that my x random variable exceeds the retention limit. So here we are doing something similar, where I'm defining that the probability that I will observe a claim on any particular risk is qj. So that qj is something which basically is the probability that I'll observe my n as 1. So again, when I'm talking about number of claims here, it is denoted by nj. So nj denoting the n for any particular number that this j will take. Does this make sense to everyone? So this is just how we define the individual risk model. And now let us see how we really play around with the moments and everything else basically that we generally care about. So remember, here I'm defining my aggregate claims with Y instead of S, okay? So what I'm going to do here now is, I'm going to write, I am audible, right? Does anyone want to ask something? Yes, Isha?
Ma'am, can you go back to that screen for just a second? Actually, I had some network issues.
Yeah, sure. Any query? Is my audio clear? I mean, is there any break in between? Because I can see my lights fluctuating, but I don't know if my voice is clear to you guys or not. Can anyone confirm?
It's clear, ma'am.
Okay, thank you, Saudi. Okay, so moving on to defining basically in mathematical terms our individual risk model. Let us say that I'm going to write my yj as xj times nj. So remember I said that nj could only take two values, either 0 or 1, right? So I will essentially get to know what is my value for yj. It will either be 0 or xi, right? So that is how I'm defining my claim amount. So this is basically my claim amount. And when I'm talking about, okay, so I think essentially what I should have been writing here would be something like this. So I'm still taking it as S, and I'm just gonna write y1 plus y2 till yn. And what I'm gonna do now is I'm just defining my x variable, so not playing around with the notations. I have my x variable denoting my claim amount. So it still denotes claim amount, and my nj denotes the number of claims. Okay, and we know this can either be 0 or 1. Okay, so I've defined my aggregate claim amount again as S, which is addition of all these Y's, and Xj and Nj still denote my claim amount and the number of claims. So now what I'm going to do is I've defined my another, not exactly defined another, but just written Y in terms of the claim amount and the number of claims that can incur. So this is one particular contract, one particular risk that I'm looking at, and the amount is defined by the claim amount, of course, depending on whether you observe the claim or not. So it can either take value 1 or 0. So that's there. So now let's say if you, I'll just make some assumptions again about the X random variable. So let's say the assumptions here are that it follows a particular CDF, which is denoted by f of x. It has mean mu j, and it is variance, which is denoted again by sigma j square. So I was talking about variance, so it's sigma j square, all right? And again, when I'm talking about claim amounts, these again are independent and they need not be identical. So they can be identical, they can't be identical. It's just not necessary. But again, remember this assumption still holds true that my nj and xj are independent. So this assumption still holds true, and this is something that we know about our x guy. Okay, so that's it. And again, the way we defined our s, we can write it as summation over all the yi's, where my I takes values from 1 to small n. So remember, we're comfortable with small n here. And when I said that, my nj, so the probability that I will observe a claim, which is the probability that I'll see a success in the way I'm defining now, makes me write that my nj follows binomial with 1 and qj, because my n can at max be 1. So it's basically following Bernoulli with the pi as qj. And Bernoulli is what? A binomial with n equals to 1. So this is all the information I know up until now, right? And okay, let me just maybe write that this was derived from the fact that I observe probability of nj is 1 as qj. Okay? Yeah. So now let us try and derive the expectation and the variance for our S. And even before we do that, let us do that for y's, and then we can just sum it up across for all the y's and we'll get the expectation and the variance for our S, right? So let me now write expectation of, give me a minute, guys. Yeah, so now I'm gonna write my expectation of yj. So this is my random variable yj, and this is the value I assume it's going to take. So what do you guys think I should do first? The most usual thing that we do, right? It will be expectation of xj times nj. So I just replaced my yi. Maybe I just shouldn't. Maybe I should just, write it all like always. So I'm just gonna write it as a random variable. So I'm figuring out expectation of my yj here. And I know I can replace my yj as xj, nj, the way I have defined it over there previously. So I can easily replace this, right? And now again, using the fact that my xj and nj are independent, what I will do is I can basically rewrite this as expectation of xj times the expectation of nj. Because these are really independent. Does this make sense to you guys? So now can you tell me what should be the answer here? What is my expectation of xj? Anyone? Okay, I wasn't muted. What is my expectation of xj here?
Mu j.
Mu j, exactly. Thank you very much. And what is my expectation of nj here?
Qj.
Qj, exactly. So it's just my binomial success rate, which is p, because my n is 1, right? So it would essentially have been n times p, but here my n is just 1, so it's just going to be p, which is qj here. So that's it. Next up, we have to figure out variance. So let's say if I want to write my variance of yj, what do I need? I need expectation of yj squared minus expectation of yj the whole square. So this we have, this we don't have. So let us try to derive that. So now I care about
Ma'am,
expectation. Yes.
I didn't understand how expectation of xj is mu j.
Oh, that is an assumption. So I have just written some assumptions here that my expectation of xj, I'm defining it as qj. This is my variance of xj, and this is my random, basically defining it by capital F, the
Okay,
CDF of
ma'am.
it.
Okay. I must have
Yes.
missed out on that part.
Oh yeah,
Thank
all
you.
right, no worries. So now what we have to do is figure out expectation of yj square. So what should I be writing next? Anyone? Expectation of xj square and nj square, right? And again, because these are independent, I'm just gonna separate them. So again, I have expectation of xj square times the expectation of nj square. So do I know my expectation of xj square's value? Anyone? What will be my expectation of xj square?
Sigma j square plus mu j square.
Exactly. So this is just basically variance of xj. So basically it's this. So you will just add up expectation of xj the whole square, which turns out to be sigma j square plus mu j square. All right. And what about the other guy? How will I rewrite this? Expectation of nj.
Qj into 1 minus qj plus qj whole square.
So you mean qj into 1 minus qj plus qj the whole square, right?
Yes.
So what will it be? It will just be qj, right? Qj square will cancel each other out. Right?
Yes.
So again, so for this, I mean, you can do this as well, or you can also observe the fact that my nj is essentially nj square. So my value can either be 0 or 1 for my nj, and if I square them, it will either be 1 or 0, right? So this is for nj and this is for nj square. So essentially, my expectation of nj square is nothing but expectation of nj, which is why you see that qj here for expectation of nj and qj here for the expectation of nj square. But that is, I mean, you can still use the formula and get the correct answer. So yeah, that's it. And now let's say if I have to write my variance of yj, what would that be? That would just be the addition, I mean this plus this guy. No, this is the multiplication. So what I will have is sigma j square plus mu j square times qj, and I'll be subtracting this guy square, which is mu j qj square. So does this make sense to everyone? Any doubts with what I have written? Maybe I should just do, so this guy corresponds to this guy here, which is all of that guy. Okay. Yeah, so I hope this part is clear to everyone. But again, is this what we are looking for? No, right? We only have expectation of ij and variance of ij. What we are looking for is expectation and variance of S guy, which is our aggregate claim amount. Right? So again, we'll try to see what happens. So if I have to, let's say, figure out expectation of S, how can I rewrite it as? It will just be expectation of summation of all the i's, where I goes from 1 to n. And again, I'll just do the usual trick of taking the summation outside and expectation of I will go inside. So again, remember, why can we do this trick? Because this does not tend till infinity. So there are some regularity conditions which we basically don't have to care about here. But again, if you go on to study theoretical econometrics, then you will have to basically care about this a lot. And not every time you would be able to exchange this. So that's there, and you will just have summation of I going from 1 to n. So, okay, we used j, right? Yeah, it's just a matter of notation. You'll have mu j times qj. And this is basically your expectation of S. And similarly, for the variance of S, you will do, I mean, just the summation again. So j goes from 1 to n, and you write the same thing again. So it is qj sigma j square plus mu j square qj minus. Okay, so basically you can just summarize it as this 1 minus qj. Does this make sense to everyone? So with the variance part, actually, I haven't really done anything. What I've done is just taken this qj inside here, and I'll have mu j squared qj here and minus mu j qj squared. So I'll just be taking this mu j squared qj common, and I'll be left with this one extra square. So 1 minus qj squared qj. So that's all that I've done. Any doubts so far? I'd really like a yes or a no.
No, ma'am.
Thank you, Savi. So again, now if I ask you guys, I mean, we've derived the expectation of S, we've also written the variance of S. What distribution does my S follow? Anyone? What is my distribution of S? So so it's nice, I don't know, maybe it's fortunate or unfortunate. The computing of the distribution of S can be complicated. So it happens that only when we know that the variables, which is Nj here, are identically as well as independently distributed, then and then only you can specify the distribution of S. And if that is the case, we know that our Nj is a binomial random variable. So my S would just be, sorry, not my S, my Y would be what? Compound binomial distribution, right? Because the way I'm defining my Y is just Xj times Nj. And again, if we say that, these are all identically distributed, I mean, not even N, I mean, not only N, but also X, then what will happen is you will just forego all of these subscripts, and instead of this summation, you will have an N over there. So let me just maybe write a note here. If everything is identical as well, what will be my expectation of S? Anyone? How will I be writing my expectation of S? So I'll be foregoing the writing of this subscript here, because this basically denotes different risks. And now if I'm assuming that all of these risks are also identical, then I don't necessarily have to write any subscript to define or denote one of those. So what I'm going to do is I'm adding up n of these. So n times mu times q, right? And the similar thing I'm going to do here as well. So again, it's a summation n times. So it will just be n multiplied by all of these things without their respective subscripts, plus mu square n q1 minus q. So this is, so this was the theory of individual risk model, I would say. It's really not complicated, because again, deriving the distribution of S is a bit complicated in actual life, so you don't have to do it manually over here. But we'll just have a look at a sum now, which will give you some idea as to how to go about solving questions from exam point of view. So let me just share my book. Yeah. Yeah, so let us try to solve this 20.6 question today. And I think it's a really good exercise, and there's some, so you see, right, that they have defined some QI here. I hope it is QI. I guess it's QI. Yeah, so I want you all to read the question first. So read the first part of the question. Can anyone read it aloud for everyone of us? Any of you? Prajakta? Can you read the question for us?
So the question says a portfolio consists of 500 independent risk, and for the ith risk with probability 1 minus qj, there are no claims in 1 year, and with probability qj, there is exactly one claim. For all risks, if there is a claim, it has mean mu and variance sigma square and the moment generating function mt. Let T be the total amount claimed on the whole portfolio in 1 year. Question 1 asks us to determine the mean and variance of T.
Right? Okay, so maybe what we can do is, first of all, we should summarize all the given information in the question. So, okay, first I would say you all take a screenshot of this question. I mean, I guess it's already there in the WhatsApp group also, right? Yeah. So let me just head over to this. And what we can do is, so let us try to define the question. So the very first line of the question specifically mentions the number of risks we are looking at. And that is a clear giveaway that we are looking at an individual risk model, right? So what we have is n taking a value 500, right? And the next line talks about the distribution of n, which again can be summarized as the probability that my ni will observe no claim. So can anyone tell me what should I write there? What is the probability that I'll observe no claims from what you read of the
1
question?
minus qi.
Exactly, Isha. So it's going to be 1 minus qi. And what should I be writing here? Savri, can you say that?
QI.
Exactly. Thank you very much. So that's it. And again, just to be I'm just going to write that this has to be from 0 and 1, between 0 and 1. Okay. So, and I guess the next bit of information we had was about expectation of x, which was denoted by mu. Was there any subscript to it? I guess no. And for variance of x, we have m sigma square, and here we have mt, which again denotes the MGF of our x. All right. So now the last line says that T is the total amount claimed on the whole portfolio within a year, right? So to start off with, let us define RT in terms of the claims from each of the policies. So again, we have to assume any random variable. So for now, I'm going to take it as Y to denote the claims from each policies. So my T is going to be Y1 plus Y2. What should I write here? Anyone?
500.
500, exactly, because we know the number of claims we have. Sorry, we know the number of policies we have, right? Not the number of claims, because these YIs can also be 0, right? Okay. So the very first question asks us to calculate expectation of T.
Ma'am, if we are taking the individual claims as y1, y2 and all, then it should be expectation of y above, right? Or is
Expectation
that
of what?
something else? Like
Wait,
above mu and sigma square.
yeah. So actually, so remember, I'm still denoting my claim amount as X. I guess there was a bit of network issue for you, right? So let me just go back to this slide. So I redefined this. So I again said that my S is the aggregate claim amount that I'm looking at. And this YIs pertain to the claims from each of these policies. And XJ denotes the claim amount and NJ denotes the number of claims from each, I mean, basically for each particular claim, for each particular policy. And what I did was, so remember I have defined my Yj as Xj times Nj. So my Yj is just a random variable, which denotes the total claim amount from one particular policy. But that itself is made up of two random variables. One, not exactly, I mean, yeah. So what we have here is Xj times Nj. So xj is denoting the claim amount, the severity of the claim, and nj denotes the frequency of the claim, which can either be 1 or 0, nothing else.
Got it, ma'am. So here we are only considering the claims that have actually happened. So that is why we are taking y separately, right?
No. So this y can also be 0, right? Because, so let's say if my nj takes a value of 0, what will be my value of yj? Given that I'm defining it in such a
0.
manner? 0, right? So here we aren't, discriminating against the claims which will which will give us a value of 0. So we're talking everything in perspective of the direct insurer's company, and my y can actually take the value 0 as well.
Ma'am, but then why even write it separately?
Why even write it separately? So I would say, that is just because we know something about X, we know something about N, right? So to start off with, we know that okay, forget about Y. Let us say we have X, we have N, right? So we know the number of claims and we know the amount of claims, right? And now if you have to summarize your aggregate claim amount, what will you do? You will multiply the claim amount with the number of claims, right? So it could either be 0 or 1. You either incur a claim or you do not, right? So what you will be essentially writing is that S equals to x1n1 plus x2n2.
Didi.
Yeah. So what you will be writing is essentially is x1 times n1 plus x2 times n2 and so on, right? So it's just a matter of notation again, I would say. So instead of writing xn every time, what you're doing is you're denoting xn multiplication together as y. It's just a matter of notation, nothing else. And maybe to make these calculations a bit easier, but again, you can do away without writing y's. You can simply ignore y and choose to write x times n every single time, and it wouldn't affect anything.
Okay, ma'am, got it.
Thank you very much for asking that question. Anything else? So it really makes me happy if any one of you asks the question, because then I know that you are thinking. You're not just sitting and listening to me dead. So, okay, that's really good. And so then let us try to see the expectation of T. So again, I've defined my T as Y1, Y2, an addition of all these. So I'm just going to write my expectation of, so instead of T, I'm going to write this Y1 plus Y2. So on till Y500. And using the fact that these are independent, again, I'm just going to separate them. So what I'll have is expectation of Y1 plus expectation of Y2 and so on till expectation of Y500, right? And okay, so now we really don't have to worry about anything. We have already derived our expectation of Y, our variance of Y, and everything else, right? So remember from the previous steps, what was my expectation of yi? It was mu y times qi, right? And what was my variance of yi? It was qi. Oh, okay, so we don't have subscripts here, right? So again, we have to be mindful of what the question is asking us of. So we really don't have subscripts here. So you're just gonna just write mu. And here we have qi sigma square. So we have subscripts for q. So we have qi sigma square plus qi times 1 minus qi times mu square, right? So now if you have to write expectation of t, it is just a matter of writing a summation and expectation of yi as it is, where I goes from 1 to 500. And similar thing you're going to do for the variance of t. Basically summation of variance of yi. So yeah, just write all of that thing again. Okay, so I guess you can do this again. Why? because my risks are independent. So this is really easy, and this is basically just the theory part, just doing it again for the sake of this question. So any doubts with this? Anyone? Any questions? Any lingering thoughts? No? Okay, so then let me just go back to our question and let us see what the question asks of us. So you guys just got 4 marks, by the way. Congratulations. So now we'll try to have a look at this part of the question. So Mihir, can you read the question for us? The paragraph, I would say, and the question as well.
Yes, ma'am. The amount claimed in 1 year on risk I is approximated by a compound Poisson random variable with Poisson parameter Qi and claims with the same mean mu, the same variance sigma square, and the same moment generating function mxt as above. Let T bar denote the total amount claimed on which whole portfolio in 1 year in this approximate model. Determine the mean and variance of T bar and compare your answers to part 1.
So what comes to you guys' mind first of all after reading this question? How should I proceed to solving this? So again, we really don't know much, right? So what is the change of information in the first question that we solved and the question that we're looking at now? What is the change in the information?
Distribution of Ni.
Exactly, Savri. So now the distribution of Ni has changed. Previously, what was the distribution of Ni?
It was binomial with parameter n is equal to.
So it was binomial with parameter n equals to 1 and my rate of success was Qi, right? So the probability that I will observe a claim was Qi, which is the rate of success apparently for us. And what's here? What does my n follow here? Ni?
Poisson distribution.
Right? So it follows now Poisson distribution with the parameter Qi. So Qi is again the rate at which claims occur, right? And in the previous question, Qi was the chance of observing a claim. So what change do you guys think will happen in this part to expectation as well as the variance? Maybe expectation we can't really say on the look of it, but what do you guys think will happen with the variance? Will it increase or will it decrease from what we had in the previous question? So we have to be mindful of what's changing, right? Because that is going to dictate if there is any change in the variance or not. And if yes, what kind of a change? Will the variance increase? Will it decrease? Or is it going to stay the same? So
Over here, can we say that n can be greater than 1 also now?
yes, that is a very, very keen observation and a very good deduction, I would say. Well done, Isha. And what does that say? So now we know that my n can also be
The
greater than
variance
1.
will increase in this case.
Exactly, and that is what we will derive. So that is precisely what this comparison is about. So now you know that my n follows positive with the parameter qi. So there is no bound on my values that n variable can take, right? It is no longer limited to 0 or 1. It can be 0, 1, 2, 3, anything. So now let us see what happens. I mean, that is actually what we're going to see. So let us derive it mathematically, which is again, a bit boring for me to write because it's not numbers, it's just mu, q and all the stuff, but I'll write it. So, okay, the thing that's changing here is that now my ni follows also with qi, okay? So again, I'm going to define my new random variable t tilde as, so instead of writing y's, now I'm just going to write c, which is to denote the claim amounts for this new random variable. Okay, so now what do I have to do? I have to take its expectation and its variance, right? So expectation of t bar, I'm just going to write it as expectation of c1 plus expectation of c2 and so on till expectation of c500. Okay, so again, what is my expectation of c here? Anyone? So the way I'm defining my c is not really changed anything. Yeah. So what will be my expectation of CI here? Anyone?
qi into mu.
Exactly. It's going to stay the same as it was for our yi. So we see that expectation of t tilde is what? It will just be summation from I1 to 500 mu times qi. And maybe you can take this mu outside as common because I mean it's just a constant, does not depend on I. So this is only a summation over I, but it's fine if you just leave it that way as well. So if you check from the previous case, that was the exact thing that we had. Mu qi would be here, right? So expectation hasn't changed. And let us look at the variance now. So variance of t tilde will again just be, summation I from 1 to 500, variance of CIs. So let us try to see what is the variance of CI now. Anyone? So what is the formula for variance?
So it will be Q into sigma square, which over here is, okay, no, it will be that only, yeah. Plus Q1 into 1 minus Q1 into mu square.
Does everyone agree with what I've written on the board?
No, ma'am.
Why?
Ma'am, that was for with binomial, right? Here the distribution will be Poisson, so the variance will change.
Yeah, and what will be the variance?
So the
Sigma.
sigma square and mu square will be the same, right? Basically,
So this was,
sigma square equal to mu.
wait, what did you just say, Isha? Sigma square will be equal to mu. Why?
Poisson distribution, right?
Oh, so wait, what variable follows Poisson distribution? N or X?
N, right?
Yeah, and what is my mu and sigma? Moments of
of X.
X. So you can't really say that, mu is going to equal sigma square, right? Because that is some information about X. And we only know that my N follows Poisson distribution. So what do we know? We know that expectation of Ni is equal to variance of Ni, which is equals to the rate Qi, right? So here I have Qi. And here what was this? This was my variance of Ni, right? And this is for the binomial case.
Okay, got it.
Got it?
So it will be Qi into sigma square plus Qi into mu square.
Exactly. So this is the correct one. Very good. So now we have it. And this is not for our case. Yep. So now I'm just going to rewrite that thing here. And what do I get? I get summation I from 1 to 500 Qi sigma square plus Qi mu square, which I can again summarize as sigma square plus mu square taken outside as common, summation Qi, I from 1 to 500. So this is my variance of T tilde, right? So can you guys see from the previous case, which one has a higher value? Can you compare? Okay, so maybe we should really write out the answer for this one as well. So for this guy, we would have, get this thing, right? So we'll have sigma square summation Qi plus mu square summation Qi times 1 minus Qi. So let us check one by one. We have sigma square summation Qi. And here also we have sigma square summation Qi, right? Sigma square summation Qi. So this is same. And the next thing that we have here is mu square summation Qi. So if I go back, what do I have here? I have mu square. But instead of summation Qi, I have Qi times 1 minus Qi. So how should I compare this thing now? How should I compare this two? So what will I be comparing? Yes. So basically I'm comparing this equation with this equation here.
Ma'am, can we split the bracket from the first equation? Can we write it like Qi minus Qi the whole square? Sorry, Qi
Yeah.
minus Qi square.
Yes, you can do that. And then what will happen? You'll be
Then we
subtracting
can,
something.
yeah, then we can say that we have an additional term mu square, that is minus mu square into Qi square. So basically we can just see that there is a minus sign, so it will be smaller.
Yeah. So again, if it were not mu square there and only mu, you couldn't have been able to say this, right? Because we know now for a fact that even if my mu is negative, for some reason, I mean, which of course it wouldn't be because it's a claim amount. So just discard that fact. I just put my another hat on. Okay, so otherwise, let's say if we weren't looking at the claim amounts and if the similar condition were supposed to be there, we wouldn't have been necessarily able to say what will happen and which will be the largest among these two if it were not mu square and only mu, right? Because agar mu negative ho jayega, so negative negative will become positive. But now here you can compare because you do know that mu will always be positive because what is mu? Mu is the mean of the claim amounts, right? And my claim amounts are always going to be positive. So my mu will also be positive. So yeah, that's it. Let's see how many marks we just got. 4 marks. A bit less for all the work that we did, but yeah, worthy.
Ma'am,
Okay. Yes.
and if not that technical, then can we also just say by observation that Qi lies between 0 and 1. So Qi into 1 minus Qi will definitely be lesser than the original thing, right? It will be lesser than
Yes. So I mean, that is the first thing that would come to my mind. So I wouldn't even care about splitting it because I know for a fact that my Qi always lies between 0 and 1. So Qi times 1 minus Qi is, of course, as you rightly mentioned out, is going to be less than 1. I mean, less than Qi. Because 1 minus Qi will always be less than 1. Does this make sense to others? Do you understand this reasoning?
Yes, ma'am.
Okay, well done. So let us move to our next bit of the question. And who would like to read this for me? It's only a one-liner. Savi? Do we have it?
Assume that Qi is equal to 0.02 for all I, and if a claim occurs, it is of size mu with probability 1. Part 3, derive the moment generating function of T and show that T has a compound binomial distribution.
Okay, thank you very much. So again, let us try to summarize what the information we have. So who would like to help me with summarizing information for this question? Do you want to have a look at the question once again? So now they have defined for us the value of Qi, and they're saying that if at all a claim occurs, it's always going to be of size mu. So you see how they have, mentioned the size mu and not something else, because only if you take the size mu for each of the claims, you're going to get the mean as mu, right? Otherwise, the claim size cannot be the same. So that's true. And it says it's going to be mu with probability 1. So now we have to figure out the moment generating function of t. And yeah, for the moment generating function of t tilde as well. So let's try to do that. These are only for 2 marks. So you see that, we have to prove. So the very first thing that you can do is maybe open up your table booklets and have a look at the MGF of compound binomial distribution first, so that we get an idea of what kind of answer we are looking for. So just keep that in front of you, and this is kind of good only. So let us try to derive. So the information I have now is that my Qi takes a value 0.02. That's it. And my MGF of T is what? That is my question. So I will prove that it is compound binomial distribution. So let us start. MT of T, expectation of e raised to small t big T. What should I be writing next? Probably expansion of the T, right? So e raised to small t, y1 plus y2, so and so till y, 500. Then it's basically same stuff every single time. So I guess you guys should really be familiar with what I have just done on the board. Okay, so my next step would just be m y1 t times m y 500 t. Does this make sense to everyone? Yes or no?
Yes, ma'am.
Thank you, Mayor. Okay,
Yes,
so
ma'am.
now, thank you. So now have a look at your table booklets. So remember, we have to prove that it is a compound binomial distribution. So what we have on the board, does it look anything like that? No, right? So what should we do now? What is the one, sorry, what is the one bit of information that I haven't written in black on the board from the question?
If a claim occurs, it is of size mu with probability 1.
Yeah. How can I write that information in mathematical terms and using basically the variables that are there in this question?
So can we say probability y equal to mu is equal to
Yeah.
1?
Okay. What does this mean? How can I use that information now? And what do others think about what I have written on the board?
Actually, ma'am, can we say that probability y equal to mu given that it is not 0? So they are saying that if a claim occurs, then it is of size mu.
Yeah, right. So if and only if a claim occurs, so let's see what are the values that y can take. It can either be 0, right? Or there can be some claim xj and nj is 1, right? And what does question say about nj? That if at all it occurs, it's always going to be of the size mu, right? And what is the chance that you will observe a claim? 0.02. So what will this be? 1 minus 0.02. So do you guys agree with what I have just written on the board?
Yes, ma'am.
Yes. So over here, we know that this is the value of my qi, right? So let us forget about this for a while. And what I'm going to do in the classroom is just derive a general version. And basically, we do not know the value of qi. I mean, it's basically not going to change a lot, but just to show you guys. So I'll rewrite this as a multiplication from I going from 1 to 500 of various yi's, which I'm going to rewrite as expectation of e raised to t yi. Okay. So again, what I can do here is pi I going from 1 to 500, I will substitute instead of yi, ni, xi, and t should be as it is, not forget about t. So this is 1. Okay, so now you see what I have to do is I have to take expectation of e raised to ni times xi, right? So what we know about ni is that it can only take two values. It can either be 0 or it can be 1, right? So what I will have is, instead of this expectation, so I'm writing now for this expectation, okay? So this expectation can be written as, so first I'm going to take into account the probability that my n takes a value 0. So what will I have? Expectation of e raised to 0, which is just 1, right? Plus probability that my n takes a value of 1. Then what do I have? Expectation of e raised to t mu. Do you guys agree with this? I mean, actually not even mu. I mean, you cannot substitute it. What I'm going to have here is just x. Okay. And now to account for this pi, I'm just going to raise it to n. Because I know that all of these are actually what? Identical. So what do I get? Probability that my n takes a value of 0 plus, this is just 1, probability that my n takes a value of 1 times, what is this? This is just mxt, right? And what am I going to do? Raise this whole thing to n. So what do I get here? What is the probability that I observe my n is 0? 1 minus qi plus the probability that I observe my n is 1 is just qi. And what can I rewrite this as? Again, I'm going to rewrite this as e raised to ln of mxt. And this whole thing is raised to n. So now you see it looks exactly how a compound binomial's MGF would look like, right? Are you guys there with me? So remember, for compound binomial, basically for our T to have MGF would be what? Remember we did something like this. Yes. Does it look a bit like that? So instead of T, I have log of mxt, right? And this is the probability of failure here. So apparently here Q is the probability of success, which is usually the probability of failure in the generalized sense. But this is the probability of failure here, and this is the chance of success, which is P, and this is Q, right? And you can also do it using this. So basically, if you know that, y takes on these values, you can easily derive the value of myt. So what is my myt? It's just expectation of e raised to ty. So what you're going to do is write 0.98, which is this, times expectation of e raised to 0, which is the value of y, plus 0.02 times expectation of e raised to, so t mu. So what you can do is maybe ignore the writing of expectation here and just write e raised to t mu, because that is the value that it's going to take, right? And again, I would say here also, so because expectation is taking the probability into account and then times the value it's going to take, which is e raised to 0. So this will give you something like 0.98 plus 0.02 e raised to t mu. So it's just become 1 here. And now if you have a look at your MTT, what you will have is this thing raised to 500, right? So again, it is just similar to what we saw.
Ma'am,
Yes, Isha?
so over here, by observation, we can say that y follows a binomial distribution, right? With parameters, so n will be 500 and qi, whatever value they've given us, 0.02. Can we say that?
Yes.
So can we like use that as something? Because
Yeah. So what we can do is instead of deriving the whole MGF for y, you can just have a look at the MGF of a binomial distribution and do it in the same manner. You will get the same answer, right? So mu is what you get for the success, right? Which has a chance of 0.02. So if you have a look at page number 6 of your table booklet, your MGF would be what? Q is 0.98 plus 0.02 times e raised to t, right?
ma'am, but here we got e raised to mu t, right? So like I'm not understanding that part.
Oh, so, okay. So see, what happened was here we don't have a choice between 0 and 1. We have a choice between 0 and mu, right? So you have to take into consideration the value of x as well. I mean, the value that your y takes. Generally, when we are looking at n, right, which is binomial, we see that it can only take values 0 or 1. But here, it can take values 0 or mu. So if it were 1, then you would just have e raised to t, right? You wouldn't have mu there. So now because you have mu, I mean, that is the whole reason you will have to derive. Yeah, that was a really good observation. So that is the whole reason you have to derive this.
So from the step where we've written pi of pi 1 equal to 1, I equal to 1 to 500 expected value of e raised to t into yi. So that is the pi of all the MGFs of y, right?
Yes, yes.
So there can be directly put in the formula from the table booklet with the values of q, and then so we'll have to justify there that in normal binomial we consider the values as 0 and 1, but here they have specifically given us as 0 and mu. So
Okay, okay. Yeah, so you will have to do that, but you can only now know because you have derived it that you will get e raised to t mu, right? Otherwise, you wouldn't have possibly guessed, right? That you don't have 0 and 1 and you have 0 and mu. So now you know the fact. And now if you just write it and, if you explain it properly, then I think it does make a good case. So as long as you explain what you have done and it is correct, then I would say there is really no issue with what way you arrive at the correct answer. As long as it makes sense. And in this case, it does make sense. So you can do that.
okay, ma'am.
Yeah. Thank you very much. This was a really healthy discussion, I would say. What about others? Any questions, suggestions, comments? Ready to derive the MGF of T tilde? Okay, so now I want you all to derive the MGF of T tilde. Maybe I'll also do it on the board, but yeah, let's see. It's not going to be really difficult, right? Or maybe try to let us just do it together, I would say. So this is our fourth part of the question, which asks us of MGF of T tilde. Okay, so the very first thing I'm gonna write it as e raised to T tilde. And again, so you're just gonna get the same thing, right? So I'm just writing it directly. And this will be what? Expectation of e raised to T. And now instead of y, I have CIs. All right. So now what do we have to figure out? We have to figure out MCIT. What do you guys think should be happening next? So how should I write my MGF of CI? First of all, let us start with, do we know information about CI's distribution? Anyone? How am I defining my CI?
xi into ni.
Yes. Anyone? What do we know about MCI? So this is all the information we have, right? Oops. Yeah. Yeah, I guess. Oops. Yeah, there you guys go. Anyone? So what do we know about CI? Am I audible?
Ma'am, it's a compound Poisson distribution.
And who was that?
Savri.
Why do you think it should be a compound Poisson distribution?
Ma'am, n is given as n will follow in tilde, n is Poisson, right? So Ci will be compound Poisson.
So remember, whenever we said that S is some compound distribution, what did we had? So we had something like, x1 plus x2 till xn, where my n wasn't really known. And that is when we have compound Poisson distribution, right? But here what we have, we know our n, right? Or do we not? So where is the information we have about T tilde here? Oh, okay. So wait, what does this line say? Can someone read this first line for me? Anyone? I'm surprised. Isha, would you like to read the first line of this paragraph? Only up until here.
The amount claimed in 1 year on risk I is approximated by a compound Poisson random variable with Poisson parameter Qi.
Right? And what did we do? We didn't do that, right? From what I remember, we said that my NI follows Poisson QI. Do we really have an NI here? So the information that I have is that my CI follows a compound Poisson distribution. That is what they have given us in the question, right? It's in the question itself. So the information that I know here is that my CI is compound Poisson distribution, right? So what's going to happen is I cannot define my CI as XINI, and this won't be NI. So what I will have instead is my C will be addition of x1 plus x2 up until xn, where this n actually follows Poisson with Qi, because that is when I will have my C as compound Poisson. Do you guys get it? So the question actually, so maybe if you guys want to read it again, go to the question again. So the question says that the amount claimed in 1 year on risk I, which we denote as CI, right? That is the amount which is claimed in 1 year for the risk I. They're saying that it is approximated by a compound Poisson random variable. So they've actually mentioned in the question the distribution for our guy C. So that will help us to write C in terms of addition over the sum of claim amounts, which I'm denoting here as x1 plus x2 till xn. And because I know that whatever my distribution for n will be, that is the distribution with the compound added to it, my C is going to follow. So if I know that my C is compound Poisson distribution, then I know that my N is going to follow what? Poisson distribution. with the same parameter qi. So let me see if we have, yeah, so we never really used ni anywhere else. Yeah, we did. So again, this shouldn't be ni, this shouldn't be ni, okay, and this also shouldn't be ni. I think I should just erase all of this. If you have any doubts, please ask me, okay? I'm sorry, even I ignored the fact that what was given in the question was actually that C is compound boson. Did you guys realize the mistake I made? Take some time, maybe a minute or two. Do let me know if you understand or if you do not. Are you guys there?
Yes, ma'am.
Okay. So do you get it or not?
Yes, ma'am. Understood.
Okay, thank you, Meir. What about others? So Savri, what you said was actually
Yes, ma'am.
correct. Yeah, RCI does follow compound boson. Okay. Prajakta, Isha, what about you guys?
Yes, ma'am, understood.
Understood.
Okay. Okay, all right. So now that we know our CI is compound phosphor, then this is really easy, right? There's nothing much. So if I know that my CI, so let me just write it again here, is just x1 plus x2 up until xn. Oops, right? So how can I write my MCIT as? It will just be mn log of mx IT, right? Does this make sense?
Yes, ma'am.
Yeah. So Isha, now can you tell me what will be the distribution of x? What is the value that my x can take here?
Ma'am, x can take any value, right?
What is my x?
X is the amount, the claim amount.
Yeah. And maybe try to read the question again. What did it say about the claim amount? Would anyone like to help Isha?
And the value of x will be mu with probability 1.
And why do you think so?
And because it has been given that if claim occurs, it is of size mu with probability 1.
Exactly right. So here, I mean, not for this part of the question, but for the rest of this, we do know that if at all a claim occurs, it's of the size mu with probability 1. So my x, which is the claim amount. So remember, Isha, when you said that my y is going to take value mu with a chance of 1, that wasn't for y. That was the case for x, right? So my x will take the value of mu with a probability of 1. Maybe I can write it as this. Does this make sense to everyone?
Yes, ma'am.
Yeah. So now if I have to figure out my mxt, what will that be? It is just expectation of e raised to tx. And if I know that my x always takes the value mu, it's always going to be t mu, right? So continuing with this, how can I rewrite this as? What is my n? My n follows Poisson distribution, right? So if you have a look at the table booklet, what is my MGF for Poisson? It is e raised to mu, and here my mu is lambda qi, right? So I have my qi here, and what will I have? E raised to, instead of t, I'm going to write log of mxit minus 1, which again I can rewrite this thing as e raised to qi. E log will cancel each other out, and I'll be left with mxit minus 1. Do you guys agree with this? So now what do I have? I'll have e raised to qi. Oh wait, so it looks like I have written it in the, it should be up here, right? Mxt minus 1. So this is all actually in the power, okay? Yeah, here it looks nice. Yeah. So how will I rewrite this as? E raised to qi. And instead of mxt, I will have e raised to t mu minus 1. Does this look like a compound Poisson distributions in GF? Anyone? So remember, actually, maybe let me write it again. So what we have is, my T is summation of C1, C2 till C500. Okay, so I know this N. But each of my C1, each of my C's is actually a sum of Xi's. Where I do not know my N. Okay, so now that I know my MGF of C, what do I have to do? I have to take this pi, I from 1 to 500, expectation of e raised to t ci And again, what would it be? So now I know the value of Qi, which is what? 0.02, right? So this is just going to be some constant because my T, mu really do not depend on I. So what do I have here? I have this thing raised to 500. So it will be e raised to 0.02 e raised to T mu minus 1 raised to 500, right? And what do I know about this guy? E raised to A raised to B is e raised to 8 times B. So what will happen here? I'll have e raised to 500 times 0.02 e raised to T mu minus 1, which is what? 10, right? Does this make sense to everyone? Yes or no? Or somewhat?
Yes, ma'am.
Yes,
Thank you,
ma'am.
Aisha. Thank you very
Yes,
much.
ma'am.
Okay. So I guess that's it about this chapter and for today as well. Next chapter is my favorite chapter. So we'll start with extreme value theory. And also for students who actually missed lectures up until now, I guess they can also attend that lecture because it's really not necessary to know the stuff that we have yet covered to study that chapter. I mean, only from the risk models chapter, I say. So again, I would encourage you all to, try and practice the questions at the end of this chapter and try not to look at the answer first and see what your mind says you to do. And then maybe I guess the actual learning will take place. So I would say that's it from my side for today. It is always lovely to have you all. So again, do let me know, if you don't understand anything, and it's perfectly fine. We can go over it again as well. Not a big deal.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.